Well, we can do them if you want. I can just post the solutions. I'm okay with either one. Start deport. So this file is in the office hour of. Hold on a second. I shared my screen, but I'll see it on my laptop. What is going on? Start broadcast. Okay. There you go. So this is the. Let me show it to you. It's 3740 office hours. Okay. You can see the title. So I think it's all. Yeah, it's all Laplace. And how many pages? So we'll do our today's session review on this one, and then I upload this entire thing, including all the office hours on Laplace and series into your learning. Sounds good? With the video. Turn your mic off. Turn your mic off before you start typing. Okay, go ahead. Whose mic is on? Okay, it's off now. Okay, guys, question. Do you want me to do the quiz questions? Or was it easy? Should be. Sanjay, go ahead and email to me right away. Like literally right now. Who has questions besides quiz questions? I'll go ahead and do the 2 quiz questions. Today's quiz questions. Who else has other questions? No one? Can we go over another power series problem? How many questions in the final? I have not made the final yet. It'll be similar to exam 2. Okay? I'll just give you extra 10 minutes. So basically, exam is going to be 130 minutes long. So start at whatever the time was it 5? So 5 to 7. So open at 5 and then closes at 7:10. So 10 minutes for you guys to submit. Or maybe I just, close it at 7. So you guys only do 100 minutes. I'll adjust it. Okay. And it only covers chapter 10 and 11. You already know that. All right, let me see. The email. Okay. Quiz 12, number 1. A sub n was 3 sub n minus 1, and a0 was 1. This was true for n bigger than or equal 1. Well, if you write down a1 is 3, a2 is 9, a3 is 27, right? In fact, a1 is 3a naught, but a naught is 1, so it's just 3. And I can do the rest. So in general, a sub n is 3 to the n. Now, in this power series, 0 to infinity, that's summation 3 to the n instead of that x to the n. Together is 3x to the n. And from 0 to infinity, And this is the power series for 1 over 1 minus that argument, which is 3x. So that's it. That was a function. We're looking for the... will we get the quiz 11 back? Yeah. Yes. Yes. Part B. What is that one? This one is a bit longer. I mean, that one was literally less than 30 seconds, right? Part A. That's part A. So that's A. That's part B. So what is that one? That one is A naught is 1. A1 is 5. And for n bigger than or equal 2, we have that equation. I'm going to go ahead and solve it for A sub n. It's going to be negative 25 over n minus 1 times n, and then A sub n minus 2, right? Out of that, I solve for A n. Well, so if you go for the even ones and odd ones, so for the first one, A sub 2 is negative 25 over 1 times 2, A naught, which is negative 1 to the first, 5 to the second, 2 factorial, right? What the... Oh, I know, because going to the next page. Does that work right there? No. Whatever. Okay. A sub 3 is negative 25, 2 times 3. A1, negative 25 times 5, 3 factorial, which can be written as negative 1, negative 1 to the first, 5 cubed, 3 factorial. Sub 4 is negative 25, 3, 4, A2. With that A2, you'll see it's negative 1 squared, 5 to the fourth, 4 factorial. A sub 5 is negative 25, 4, 5. A sub 3. With the A3 above, with that one, it's going to be negative 1 to the second, 5 to the fifth, 5 factorial. Okay? Well, you can see the pattern then. So A sub 2n, the even one, is negative 1 to the n, 5 to the 2n, 2n factorial. A to the 2n plus 1 is negative 1 to the n, 5 to the 2n plus 1, and then 2n plus 1 factorial. So the power series, 0 to infinity. Split it up to even and odd. So it's A sub 2n, x to the 2n, 0 to infinity. All the odd ones, 0 to infinity. Now plug in the coefficients. It's negative 1 to the n, 5 to the 2n, x to the 2n, 2n factorial, plus negative 1 to the n, 5 to the 2n plus 1, x to the 2n plus 1, 2n plus 1 factorial. So I want to write down more step, putting 5 and x together. So it's negative 1 to the n, 5x raised to the 2n, 2n factorial, plus 0 to infinity, all of them 0 to infinity. Negative 1 to the n, 5x to the 2n plus 1, 2n plus 1 factorial. Now we go back to table. First one is cosine of 5x. Second one is sine of 5x. So that's it. That's the function representing the power series for part B, and that one is part B, part A. question in that? Any step I need to explain more? Very straightforward, right? So if some of you says that it's easy, I believe you. I think it was easy. Objection? Okay, someone asked if we can do more power series problem. Sure. What kind of problem? What problem? And by the way, how many quizzes did we have after exam 2? I think we had 3, right? So quiz 9, 10, 11, and 12. Okay. So you can expect final questions to be similar, to these 3 quizzes in terms of the structure of the questions, okay? So I suggest you, master around those 3 quiz questions. If you want to be specific about type of questions you want to study. Okay, what problem should we do? Because if I pick one, I'll pick a simple one, to be honest. I'm kidding. I'll pick a complicated one. How about number 21? Doesn't look good. Okay. Do I like the fact that it's y0 equals 0? Let's see. So I'm going to ignore the fact that y0 equals 0. In fact, it simplifies it. Okay. I'm making it harder, but so number 21, it's y double prime minus 2y prime plus y equals 0. Let me mute the entrance and exit tone so that people get in and get out. Won't distract me. So there are 2 conditions given: y of 0 equals 0, and then y prime of 0 equals 1. Okay. In fact, this one tells us a naught is 0, and that one tells us a1 is 1. But let's ignore them at the moment. Okay. So let's solve this without giving those initial conditions. In fact, we can cheat right now and then see what kind of functions we're dealing with eventually. Think about it. The chapter 5 stuff, this is the characteristic equations: r squared minus 2r plus 1 equals 0. That means r minus 1 squared is 0. That means r1, r2, they both equal 1. So that's a repeated root. One is e to the x. What's the other one? X e to the x. So eventually we're looking for some constant e to the x plus constant x e to the x, okay? So that's y of x. So the final answer is going to be the power series for these guys. Okay, let's see if it matches. So now we solve this using power series. Using power series. Let y of x be a sub n x to the n, 0 to infinity. We know what y prime is. X to the n minus 1, 0 to infinity. And y double prime is n minus 1, a sub n x to the n minus 2, 0 to infinity. Okay. So I'm going to plug it into this equation. Double prime first. n minus 1. A sub n x to the n minus 2 minus 2y prime. N a sub n. Oh, I made a mistake. Where's my mistake? Doesn't start from 0. Starts from 1 in this guy and 2 on that one. So that one is 2. That one is 1. And must be multiplied by -2. I forgot that. -2y prime x to the n minus 1 plus y itself a sub n x to the n. That one n from 0 to infinity equals 0. Okay, so first we need to make these starting from the same power of n, okay? Or having same powers of n, so we can combine them. So that means I have to add 2 inside the series terms and subtract 2 from the first element. So it's going to be n equals 0 to infinity, n plus 2, n plus 1, a sub n plus 2, x to the n. All right, minus. Send that 2 inside. It's going to be 2 n plus 1, a sub n plus 1, right? And then x to the n plus the last one is a repeat, no change. A sub n x to the n equals 0. And all of them start from 0 by that change. Because here we added 1, so we subtract 1. We added 2 here, we subtract 2. Question? Now we can put them together. So we have one giant series starting from 0 to infinity. N plus 2 times n plus 1, a sub n plus 2, minus 2 times n plus 1. What do we have? A sub n plus 1 plus a sub n x to the n, and then equals 0. Good? Okay. This must be 0. Must be 0 for all n's bigger than or equal 0. So n plus 2 times n plus 1, a sub n plus 2, minus 2 times n plus 1, a sub n plus 1, plus a sub n equals 0. Solve for the term with the biggest index. So a sub n plus 2 equals 2. What do we have? We have 2 n plus 1, a sub n plus 1, minus a sub n, right? Over n plus 1 times n plus 2. And indeed, let's split them up. Makes it a bit easier. So 1 is 2 over n plus 2, a sub n plus 1. Do I want to do it like that? Let's see. Negative 1 over n plus 1, n plus 2, a sub n. Good? All right. And remember, n is bigger than or equals 0. Now let's write down the first few terms. If we need to, we write 5 of them. And we try to identify a pattern. Okay? So a sub 2 is going to be 2 over 2, right? A sub 1 minus 1 over 1 times 2, a sub 0. Keep it as it is. Do not change it. A sub 3 next. Basically, for this one, n equals 0, and n equal 1 goes for this one. What do we have? We have 2 over 3, a sub 2 minus 1 over 2 times 3, a sub 1. Plug this a sub 2 here. This is what we get. If you multiply by that first term, remember, basically you're multiplying 2/3 by those two terms above. So we get 2 squared over 2 times 3, right? And then minus, so if I multiply that, I get a sub 1 minus 2, 1 times 2 times 3, a naught. Minus 1 over 2 times 3, a1. Do you see that? Okay. And let's simplify them. These two are like terms. So what do we get? We get 2 squared minus 1, 2 times 3. A1 minus 2, here 3 factorial, a naught. Let's continue. You know what? That's 3. Let's write that as 3 for now. I'm not going to cancel it, okay? I'm just going to see what happens. 2 over 3 factorial, a naught. Okay. Now a sub 4. A sub 4, according to the formula above, is 2 over 4. A3 minus 1 over 3 times 4. A2. Okay. So if I plug 2/4, let me plug A3, which is this guy. 3, 2, 3. A1 minus 2, 3 factorial, A naught. Minus 1 over 3 times 4. Now A2. A2 was this guy. Right there. 2 over 2 A1 minus 1 over 2 factorial, A naught. Okay. So what do we get? I have A1 terms. I have those two. Okay. That one is 2 times 3 minus 1 times 2. And then I have 2 times 3 times 4. Yeah, that's the same. And then I have minus. By the way, A sub 1. And minus. Oh, hold on a second. I forgot to multiply. I'm regretting the problem I picked, but no. That's 2 times 2. That's a 4 factorial. And indeed, that one is going to be a 4 factorial as well. Let's do that minus, and that's also a plus. What do we have there? It's going to be that guy. Right? A naught. Okay. let's simplify here. That's 6 minus 2 is 4 over 2, 3a1 plus, I have 4 factorial right there. That coefficient is strange. Let me go up here. N equals 0, okay? And then n equal 1. We multiply by that. Then minus itself, we combine those two. What do we see here? Okay, that one is 1 over 2 factorial, so it makes sense. This one is going to be, there was a 4 missing, so that one is 1 over 3 factorial a1. I think that one makes sense, okay? And then this one, is 4 factorial denominator. That's it, plus 1. I'm confusing myself. These two, that's a plus, and these two is a minus. Let's write it this way. This should be 4 factorial minus 3 factorial. A naught. I guess that's the reason they're given A1, A naught equals 0. Term is going to be challenging. I can see that now. Let's go up there. What was the A naught that they were given? Yeah. Okay. Well, so let's apply that thing. So if you do that, these terms are going to be 0. So we do have to use. So use A naught equals 0 and A1 equals, what was it, 1? Yeah. So if we do that, this term is going to be 0, and that term is going to be also 0. But if you simplify them, this is what we see. So A, let me go back to this guy. That is nothing but 1 over 2 factorial A1. And A sub 4 is 1 over 3 factorial A1. Okay? So A2 was 1 over 1 factorial A1. A3 was 1 over 2 factorial A1. So I'm not going to write down the pattern for 5, but we can guess what it is, 1 over 3 factorial A1. We can show that A5 would be 1 over factorial A1. Okay? So in that case, A sub n is going to be 1 over n minus 1 factorial, and then times A1. And A1 is 1, so it's just simply 1 over n minus 1 factorial. That was challenging. But this should be a way to get the x e to the, e to the x1. Let's see which one this one creates. So sigma A sub n, x to the n, is going to be 1 over n minus 1 factorial x to the n from 0 to infinity. What function this represents? Oh, by the way, a naught was 0, so we have to ignore the first, the n equals 0. That means this series starts from 1. Okay. So by doing that, let's pull out an x. That means we get x to the n minus 1 over n minus 1 factorial, n from 1 to infinity. But this function is just e to the x. So the particular solution for the case when y0 is 0 and y of 0 is 1 is this guy using power series. Let's see if it matches. C1 e to the x plus C2 x e to the x, that was y. The prime of that is C1 e to the x plus C2 e to the x plus C2 x e to the x. Y of 0 being 0, that means C1 plus C2 is 0. Y prime of 0, that means C1. What? Oh, hold on a second. C1 is 0. Made a mistake here. Because this term is 0 when you plug 0. So then C1 plus C2 is just 1. Well, if C1 is 0, then C2 is 1. And yeah, it gives you the same thing. Because that term is 0 and that coefficient is 1. So it gives you the same function. Okay. That was an interesting one. Almost got me. There's a very deep silence going on. Someone says something. What? Hello?
We're all watching.
Yeah. Well, that was an interesting one. So what else do you want to do? Do you want to guys do any Laplace questions, or you are the expert in this subject?
Well, we have to know the definition, or we're going to have to use the table.
I mean, I've already quizzed you on using definition, and it wasn't a very difficult one. But just be ready, to get a simple function find in Laplace, especially piecewise ones. Those are the ones that you have to do some integration. Let's say t square or t plus 1, something like that. If t is bigger than or equal 3, and this one t between 0 and 3. Okay, one of them should be strictly less than. So something like that. And then you take in Laplace. So if this is f of t, you have to split it up, right? So it's f of t 0, 0, 3, and then 3 to infinity. E to the negative st t plus 1 dt, and then plus e to the negative st t squared dt. And the rest is integration. So if you want to use a table of integration, feel free to do that. Okay. So I'll leave the rest for you. Let's do one Laplace. So partial fraction Okay, let me see. Let's see if we can come up with a guideline. So final exam. Laplace. So be familiar with the definition. Definition of Laplace. Okay, finding transforms, just like the example we did above. To make sure you know you're able to apply table, the Laplace table, to functions and the translations of functions, okay, or transforms of functions and combinations. Combinations of functions, like e to the at f of t, okay, t to the n f of t, derivative of, or the nth derivative of t, okay, of course including the normal functions or the elementary functions: exponential, sine, cosine, sine h, sine, cosine h. 3, finding inverse inverse Laplace inverses, and for that the biggest technique you need is partial fraction. Okay, example, Laplace inverse of something like this: s to the 6 plus 1, and on top, let's see, 1 over s to the 6 plus 1. This is a very nice problem. You can do it on your own. What else? So that was for Laplace, okay? And if you know these 3 steps, you can solve differential equations, okay? So differential equations given with initial conditions. You take Laplace of it. It transforms to an equation of f of s. So you find f of s, solve for f of s, and then you take inverse of that, and that gives you the solution, or x of t, I guess. Doesn't matter. So that's why you need to know how to find inverses of, Laplace inverses, and that would be the solution. Okay. So let me zoom out. And for the power series, it's like the stuff we did. So you start with differential equation, try to find the pattern on those the series terms, a sub n's, that sequence elements, and then use the table for the okay, what else? Can we use to solve the sort of first order linear differential equations using Laplace if the initial value is not given? No, because remember when you're finding Laplace of y prime, it's going to be s y of s minus y of 0. So you do need the space. I mean, you can assume it's a constant, okay? And then when you take inverse, I mean, if you're comfortable working with that constant, not necessarily, but because think about it. Let's see. Let's say we have y prime plus, 2 first order, you said, right? First order. So let's say y prime plus 2y equals, let's say sine of x, okay? Sine of t. Okay, so here we have s, y of s minus y of 0 plus 2y of s equals 1 over s squared plus 1, okay? So we have s plus 2 times y of s equals, let's call this some, I don't know, constant, let's call it c. So it's 1 over s squared plus 1 plus c. I have to divide by the coefficient. So dividing by that, we get this, and then plus c over s plus 2. I mean, it's going to be, a constant is going to be showing up in the equation. So the answer is yes. Let me see if there's a situation when you might. I cannot think of any situation that will cause problems. So I want to take it back. The answer is yes. Yes, you can. Without initial conditions, you can. Let's see what happens for the second order. Minus 2y plus, maybe 3y equals x plus just x, okay? So s squared y of s minus s y of 0 minus y prime at 0 minus 2 times sy of s minus y at 0 plus 3y of s equals, that one is 1 over s squared, right? That should be t. Let's use t. So let's put them together. S squared plus minus 2s plus 3 times y of s. Let's call this c1. Let's call that c2. That means this is also c1. So we have negative c1s minus c2 minus 2c1 equals 1 over s squared. And let's go ahead and solve for y of s. So y of s is going to be 1 over s squared. S squared minus 2s plus 3. And then plus this thing, which is c1s plus c2 plus 2c1. I mean, even for this one, you can, but, those coefficients for the partial fractions for this one you're finding, right? It's going to be in terms of these two constants. So working with constants, like solving constants in terms of other constants doesn't confuse you. Yeah, of course you can do that. What if you're solving for two set of differential equations? You mean a system of, like, you have a system? Okay. So let's see. These are interesting questions. Let's say you have x prime equals, do you want it to be homogeneous or no? It doesn't matter. X plus y plus maybe, sine of t, and then y prime equals 2x minus 3y plus cosine t. So no initial conditions. No initial conditions. So you have s, x of s minus x of 0, which is not given. It's going to be x of s plus y of s plus 1 over s squared plus 1. Sy of s minus 2x of s minus 3. Yeah, it's doable. So this one's doable too, except, you're going to be dealing with constants. So let's go ahead and call that, maybe A, call this B. So no initial conditions means we can suppose x0 equals 0? No, not necessarily. No. Just like I said, eventually you're going to be dealing with situations like this. Like you have to decompose this fraction, but you don't have. Okay, what if A equals B equals 0? Yeah, in that case, it's doable. In fact, I think we did an exam. There was a quiz question that we did, right? Although I only ask you to solve for x of s and y of s, and then you just have to take inverse. So if you're saying A and B equals 0, that means in this case, you are including initial conditions x0, y0 equals 0. Well, in that case, it's doable. So you want me to continue doing that? Oh, so you watch this one, or even easier, homogeneous. Okay. So not even. So let's erase that. That makes it easier. So let's get rid of these. So we only have those. Okay. All right. And do you want me to continue with the same system or do you have a different system? Same? Okay. So S times x of s on the first one. So s x of s minus x of s equals y of s, right? So in this case, just y of s equals s minus 1 times x of s. Let's plug it in the second equation. So this second equation, we have s plus 3 y of s equals 2x of s. So let's plug this in here for y of s. So we have s plus 3 times s minus 1 x of s equals 2x of. Huh? Hmm. Let's see. We would have e to the lambda and then v c1 plus c2 e to d. This is what we have, right? Did I make a mistake? s, and then we have x of s. So bring it the other side. We have that, then we have this. No, it doesn't make sense. Okay. It does make sense in this sense. Because out of this, we can solve for x of s. Okay? And here's the reason. So solve for x of s is going to be, if you bring everything to one side, okay, you get negative equals 0. And then you have x of s is s plus 3 times s minus 1 minus 2 equals 0. Well, this is never 0. This is not 0, of course, right? That means x of s has to be 0. Well, x of s is, if it's 0 and you take inverse, that means x of t is 0. And I get the same thing. If you plug 0 here, y of s is 0. And then y of t also is 0. Now, let's go back to the system that we started with. So x prime was x plus y. Y prime equals 2x minus 3y. Now I have a question for you. Isn't 0, 0, functions 0, 0, a solution for this system satisfying the initial conditions x of 0 equals 0 and y of 0 equals 0? The answer is yes. But that's the most trivial solution. Okay? And here's the other one. Let's say we don't even do Laplace and we just go normal, eigenvalue eigenvector. Okay? What would we have? We would have x of t, which is little x of t, and y of t equals c1 e to the some lambda 1, even if it's complex, v1 plus c2 e to the lambda 2 t v2. Okay? Well, think about it. If I plug 0 here, right, I have, so v1 and v2, let's say this is a, b, and this is some c, d. Okay? Well, we know a, b, c, d is invertible. It has inverse. Okay? Well, think about it. When you set up the initial conditions, you get a matrix A, B, C, D times C1, C2 equals, you said initial conditions were 0, 0, right? Well, you multiply with this inverse, then C1 and C2 is both 0, 0. And if you plug them back into the solution, the solution is 0, 0, which satisfies the equation. So this is a very trivial case. So it means we should have at least one of these cases. Both cannot be 0, 0, or you should have non-homogeneity happening here. So something non-zero. So in that case, you wouldn't get a trivial solution 0, 0, if it makes sense. And I guess that's why. I guess you can make that problem. I think that's a very trivial thing you need to say. Because 0, 0, is a solution of a homogeneous differential equation. It doesn't have to be a system, even a normal differential equation, linear one. Okay, let's do one more problem, guys. You only have 5 minutes. Nobody asked questions. Beside Yogesh, you just left it to me. If you can get a hold of me by sending me email. I'm mostly at home. So if you want to get online to the meeting, we can arrange that, okay? But you have to let me know. What else? I'm gonna give you a video to you guys for one last time. How about that? And I wish I could show you my setup. I have my iPad here. This is what I write in, by the way, with this pen. And I have my textbook open here. And this whole thing was recorded. That was silly. Okay. Any other questions? The final should be simple, so I don't make it very difficult. Oh, I think that's because of the app that I'm using. So, if I think I changed the settings. Damn it. Let me see. I think if I go back to the settings, handwriting. You see, it says tap and hold to enter Zoom, or is it that one or no? Oh, it says use the pen to highlight, draw a shape, and continue to hold the finger or still down to automatically detect it. Okay, let's see if that works. Office hours. Yeah, goes like that. So if I do an ellipse, yeah. If I do a rectangle, straight line, yeah. The app is called Notability. Is the app next to my settings? That one right there. You're welcome, guys. You are welcome. That was a good semester. I mean, halfway. They didn't like the way we were doing it. Just kidding. Stay safe. It's very important. Stay home. Take care of yourself and your family members. You're welcome. You are welcome, guys. Still go do the evaluation. Criticize me. I like that more. Especially online stuff. You are welcome. I'm gonna stop recording this thing.